Okay, good afternoon and welcome back to the cryptography lecture. Let's get right back in where we left off last time. For that, share my screen. Okay. So last time we made it until the law of total probability, which we see here again. Essentially, what does the law of total probability tell us? Let's say we have our probability space, call it omega, and we have a set of events B1 until Bn, which cover the entire space, but the Bi are disjoint. So their unions their intersections are empty, which means that basically we can partition our space omega into these, let's say, B1, B2, B3, and B4, right? That's what it means that they're disjoint. There's no overlap between them. So we have a partition. Oh, sorry, this is B1. We have a partition of our space omega, and what that means is for any other event A. Now, when I draw it, this is kind of immediately clear, so I call this A. Then this partition on the space omega also induces a partition on our event or set A, right? So essentially, we can describe as A as the union of A intersect B1. Here we have A intersect B2, A intersect B3, and A intersect B4. And the law of total probability really just said, if we reinterpret it in terms of, let's say, instead of probabilities, cardinalities of these sets, it just says that the cardinality or size of A is the sum of the sizes of these A intersect BI, as what we have on the left side here of the law of total probability. If we rewrite that by the definition of conditional probability, this is just the probability of the event A intersect BI. Okay, so let's still do the actual proof just to see how these probability laws that we got to know in the last lecture go into effect. So we've seen that if, let's say, two events E1 and E2 have an empty intersection, then the probability of E1 union E2 is just probability of E1. Oh, sorry, this doesn't look good. E1 plus probability E2, right? We had that in general, the probability of the union of two events, or the OR of two events, is the sum of the individual probabilities minus the probability of the intersection. But now we have that the intersection is empty, so the probability of the intersection event or the AND event is 0. Generally, right, if we have more than two of these events, we have probability of E1 union and so forth until En is just sum of the probability of the EI, I equals 1 to n, given that these EI are usually disjoint. Yes, thank you. Someone commented it shouldn't be not equal. Why did I write not equal? I think I said they are. The intersection is empty. I don't know why I wrote it's not empty. EI Ej equals rho for all I not equals j. Okay, that's a generalization. If we have the this is partition E1 to En, and each of these each pair of events are disjoint, then we can write the probability of the union just as the probability or the sum of the probabilities of the individual events. Okay. So now using elementary set arithmetic, we have that our event A is just, well, A intersect omega, right? Or omega is the entire space. We know that A must be somewhere in omega because omega is the ambient space. So, but from the from here, we've seen that B1 to Bn cover the entire space. So we can rewrite this omega as say E1 and so forth until, oh, sorry, why did I call them E? Here we call them now B. Let's call these events B1 until Bn. And of course, this is the same as A intersect B1, union, and so forth, union A intersect Bn. And therefore, if we look at these sets here, we know that the Bi and Bj are disjoint, therefore they still remain disjoint when we intersect them with A. Okay, so it follows that probability of A is the same as, well, we've just rewritten A here. Probability of A intersect B1, union, and so forth, A intersect Bn, but now we know that these A intersect Bi are disjoint. So this is just the sum of the probability A intersect Bi, I equals 1 to n. And now using the definition of conditional probability, we can rewrite this probability of A intersect Bi via probability of A conditioned on Bi times probability Bi. This is really nothing complicated. And I think, in fact, this picture that we have here explains pretty well what's going on with the law of total probability. So this seems to be a trivial thing from the let's say from a mathematical standpoint, but we'll see this will be incredibly useful when analyzing probabilities of events that have sort of a complex description. We'll use the law of total probability to break these complex events down into simpler events. Okay, now let's do that. Let's do something like that, and let's see the law of total probability and Bayes' law in action. Now, for our example, we assume that 2 in 1,000 people in a population have a certain disease. And there exists a test for this disease, but it is not flawless. That means this test is gonna have a certain probability of error. If you happen to have the disease, or if someone happens to have the disease, then there's a 95% chance that the test returns positive. On the other hand, if you don't have the disease, then there's a 3% chance that the test returns positive. Okay, and now we come to the following. Okay, someone asked me to go back to the last slide, to this one here. Oh, was there still a question concerning this slide? Then please just speak up. Okay, good. Now, where were we? Now, let's say someone tests positive with this test, and we want to know what is actually the probability that this person has the disease. Okay, and first of all, this first point here, that 2 in 1,000 people have this certain disease. This is the we call this this is the prior probability. In other words, if you wouldn't do the test, if you don't have any symptoms, if this, let's say this disease doesn't come with any symptoms per se, then this is sort of your best guess for how likely it is that any given person, if you fix any person in this population, has this disease, right? There's roughly 2 in 1,000, then your probability is 0.02 or 0.002 or 0.2% that you have this disease. So this is your best guess in case you don't make a test. What we're interested in is the posterior probability. So without test, this 0.2% probability is the best guess you can do. Now, what happens if you do a test? Oh, something didn't. No, okay. Forget about this. I don't know how that ended up here. Okay, what we're gonna do next is we model this scenario with a probability space. And we will see that we just have to define this probability space implicitly. And how do we define it? Well, first with the, let's maybe we can draw our space. This set is omega, this set A is something small, and it doesn't really matter how we model it. The only thing that matters here is the probability or the weight of this set, which is 0.002. Now, on the other hand, we have this. We have a second event B, which is that which models that the test returns positive. Let's maybe redraw that slightly with a different color. We have our event A here, which is not drawn to scale. And now our event B, will be something like this. And what we know is that probability. So on the one hand side, let me draw this. So the green thing here is 0.0002. On the other hand, I mean, I don't want to use orange. Let's maybe use this red. Conditioned on not A, right? This part out here, again, this is not to scale. This is the area in red here is 0.03. What we actually do want to know is the probability of A given B. So in the end, it's a conditional probability. That is, when we contract the entire thing to B, we want to know what's the size of A intersect B in relation to B. Okay. Now, how do we do this? Well, for this, the law of total probability and Bayes rule are our friend. If we want to know probability of A given B, well, we don't really have so much to work with yet, but we kind of have the opposite thing. Sorry, I jumped over that. So the probability of B given A is 95%. So we have a probability of B given A and probability of B given not A. But what we're interested in is probability of A given B. So the first thing that we're going to throw at this is just Bayes' law to reverse the conditioning operation in these in this probability, right? So this is just probability of B given A times probability of A divided by probability of B. Great, let's look at this. And we will see, let's maybe use orange. This thing here, probability of B given A, that's something that we know. That's a value that we've seen already. On the other hand, we have this probability of A here. Same thing here. So these two things we have. The only thing that's missing is our probability of B. So what do we do there? And this is really a blueprint of how we're going to use the law of total probability and Bayes' law in general. There will often be something in the denominator which we still don't have. And what we're going to do in that case is we're going to expand it using the law of total probability. So we can write probability of B as probability of B conditioned on A. That's something we know, times probability of A, again, something we know, plus probability of B condition not A, again, something we know, times probability of not A, right? Either the event A or not A must happen. So what color do we use? This guy is good. We have him, that guy, or let's use the correct colors. This guy here is orange. This guy here is green. Now let's use maybe black. Black is this guy. So the only thing that's missing is probability not A. How do we find probability of not A? We know what probability of A is. How do I find probability of not A? Exactly. So someone just wrote the answer. The probability of not A is 1 minus probability of A. It's just 1 minus probability of A. And there, with that, we have everything in place here. If we plug in the values, which I won't be doing now by hand, but if we do this now, it will come down to 0.06 or 6%. So there was another question by someone. Can you please tell how you applied the law of total probability on probability B? So good. With that question, let's quickly jump back. Oops. Okay, and here we are. That's a law of total probability. My events B will now just be B1 is A and B2 is not A. If you plug these choices into the law of total probability, then but let's erase that from here, because I think here it would be more confusing. Oops, how did that happen? That's not good. Okay, oh well, good. Okay. Oops. So again, for what we do here, law of total probability, B1 equals A and B2 equals not A. All right. Okay, good. That was that. And we're really going to see that a lot, how this specific use of Bayes' law and the law of total probability, this is really gonna come up quite often in this lecture. And what we've now will introduce a concept which will be helpful in just modeling and abstracting certain things, something called random variables. So far I've always been talking about events, but in general, it will be helpful to look at events that are, let's say, events that are not just true or false, but that could, in some sense, have several outcomes. And if that's the case, we don't call these things events, but random variables, right? This is the formal definition, I think, can be quite confusing. As a matter of fact, when I saw this definition for the first time, I was kind of confused. So this thing is called a random variable. And then the definition says a random variable is a function from the probability space into some other domain called D. That's the general definition of a random variable, right? We're mapping from our sample space into some other set D, and we call this a D-valued random variable. So such a random variable takes on values in this domain D. But why is it a function? Well, the reason why we define such a random variable as a function is that this gives us sort of a nice and compact way to define a set of events, right? So this function induces several events, namely for every x in this set D, we're gonna define events EX, which correspond to the pre-images or to the pre-image of this x under this function x. So what does that mean? Let's maybe draw this, right? So here we have our omega, and then how such an event EX looks like. Think of that. Those are all the values in this sample space omega, which map to this value x, right? Under my function x, if we take some ex prime, then they map to x prime under E. So really, EX is just the pre-image of this lowercase x under my function f, x, whereas EX prime, for instance, the pre-image of x prime. Whoops. Okay, what's happening now? Oops. Okay, something. Okay, good. And for these events, EX, can you repeat EX again? So, I mean, EX is the definition of EX is written here, right? So what EX are all the elements in this set omega, or in the sample space omega, which map to this lowercase x under the function capital X. So really, we just define this function to get a set of events. Let's call this EX x1, x2. Let's maybe say EX3, and so forth, right? Every possible outcome x1, x3, x1, x2, x3, x4 correspond to different events, and an important thing here is, of course, that these events are disjoint, right? They cannot intersect, because if you have some element in omega which maps to x1 under this function capital X, then it cannot at the same time map to x2. So it gives us a disjoint partitioning. Is small omega a point in the probability space? The answer is yes. So omegas are, I mean, it's written here, right? Small omegas, they lie in here. Good. Okay. Let's get on. And now that we've defined all this, right, I'm going to ask you to forget this. So this is the formal definition of random variables, and I'm not kidding. From now on, you can safely forget how this is defined. We won't even query this definition in a quiz or mini test. I'm not kidding. I still should check with our tutors just to make sure that they don't do this. But the point I'm trying to bring home is that typically we will define random variables just directly by the probability function. So instead of actually giving you a partitioning of the sample space and trying to think of all these complex complex events, what I'm or the kind of leap I'm asking you to take is to sort of accept that from now on we will define random variables by this probability function. I mean, here call it f of x, but it will typically be of this form probability x equals x, where here x is some value in this domain D. And we will typically define random variables by their just by their probability distribution functions. In the end, we will still see alternative ways of defining random variables, namely by something called a sampler or a sampling algorithm. But for most simple random variables, we'll just define them by a probability distribution function. Okay, so I think this we have a humorous comment, but if we forget this, we will get bad stats lab grades. I'm sorry. If in the stats lab lecture they tell you to work with this distribution, I think they're actually pulling your legs. So no one works with this with this actual definition of random variables. So typically you see this once so that you have a proper formal definition in case you sort of wonder something about random variables, then you can go back to the actual definition. But in, let's say, everyday life, we're never going to use this this formal definition. We will just define random variables by their probability distribution function. And everyone does this. So this is the formal definition. Now you know it exists. We probably won't ever use it again. Okay. Now, but there's still another important concept called independence of random variables. We've already seen independence of events. And we say two random variables x and y are independent if for all x in dx and y in dy, the events x equals x and y equals y are independent, right? And now you ask yourself again, wait, events x equals x, that was just the shorthand for this ex. So for random variables, we write events often as x equals something, or x is in some set, or what not. Okay, so two random variables are independent if all, say, elementary outcomes, all events that model elementary outcomes of these random variables are independent. In other words, we have for all x in dx and y in dy, probability x equals x and y equals y is just probability x equals x times probability y equals y. Okay, now a really quick example. So for instance, just to see some notation, if x is a dice roll, then we define x as follows. Define x via probability x equals I equals 1/6 for I in 1 until 6. right here, our dx, this dx is, whoops, dx is just the set 1 to 6, the set of possible outcomes of this random variable. And since if this is a fair dice roll, then every outcome from 1 to 6 has the same probability, namely 1 over 6. Sometimes we also draw just the graph of this 8, 4, 5, 6 of this probability distribution function, and this looks like something like this, right? The probability distribution function here is just a flat function, which is 1 over 6 everywhere. And we can all, of course, now since we have defined random variables this way, we can also define events differently. For instance, what's the probability x? Let's say x is even, right? Our dice roll returns something that's even. That's of course probability x in 2, 4, 6. We can write it this way, right? But if we expand this now, this is the same probability as x equals 2, or x equals 4, or x equals 6. We said that these elementary events for random variables are, of course, disjoint. Therefore, this is just probability x equals 2 plus probability x equals 4 plus probability x equals 6. And this is, of course, 1/2, right? 1/3 plus 1/3 plus 1/3. Let's maybe write that out. So you have it here once. Sorry, 1/6, not 1/3. 1/6 plus 1/6 plus 1/6 is 1/2. Okay, this is really just as a quick showcase of how we're going to use random variables. Are there questions so far? This is an important concept, right? And you should make yourself familiar with this, how we're going to work with random variables. We probably already have something on the exercise sheets. I have to take a look at this. But this is really something you should feel comfortable with, and you should familiarize yourself with how to work with random variables. This is going to come up a lot in this lecture. This is really something that needs to be part of your elementary skill set, because that's, I mean, again, what I said in the beginning, what crypto is in a sense all about. Without randomness, without probability, no cryptography. Okay. Now, and as I said, from now on, we will omit this stupid function notation, and we will also omit the entire sample space. So everything we're going to do from now on, we will model with random variables. And so instead of defining this sample space omega explicitly, we will define it implicitly via some set of random variables. We will say, so here are some random variables we're going to start with, x, y, and z, and they're independent. And this will be enough to implicitly specify this sample space omega. Someone is asking, what does this question you just explained asked? Which question? Did I explain a question? Last slide. Last slide. No. Here there was just an example. Which question? Aha. So there's another question. We discuss independence twice in slides 11 and 19. What's the difference between them? Is it event slide 11, random variables slide 19? That's exactly correct. So here we have random variables, right? And we define independence for random variables. Earlier, we've defined random variables for events. I mean, this definition of independence of random variables is based on the definition of independence of events. But yeah, this is the, in some sense, more general definition. But there was still another question. What does this question you just explained ask? I mean, there's no question here. I just sort of showed an example of random variables, how we denote them, how we specify them, how we use them, right? So there's no question that was answered here. Okay, so from now on, let's forget about the sample space. The general idea will be the probability space will be, again, implicitly defined via a few independent base random variables. So we're going to specify some random variables and all other random variables that are going to show up in our experiments and systems will mostly be functions of these base random variables. In that sense, all other random variables of interest depend on these deterministically. And when we construct such a system or systems that use randomization, we typically do not keep track of the sample space, right? Typically we say, oh, we need another random variable to model this. Let's just pull it in. Technically, we would have to expand the sample space. That's essentially the reason why we just forget that the sample space even exists. We know we can define a sample space in the background, but we're not going to bother with this. Okay, and here's some important notation. Which the arrow actually goes the wrong side. I don't know how that happens. So if X is chosen uniformly at random from some set D, if X is a random variable and we choose it uniformly random, then we just denote this with X here. X is chosen with such a left arrow from D. So instead of saying X element D, X is in D, we denote X is uniform in D via this notation. Okay, so more examples. Let's say x1 and until xn are just independent random variables such that each xi is uniform on 0, 1. We just say each xi is a coin toss, right? Last lecture, we've defined what it means that something or what a coin toss is. Now we just refer to random variable, uniform random variables over 0, 1 as random coins. That's just a cryptography lingo to say something are random coins. You're going to get used to this. And if they're independent, we just say x. What happened there? The x1 to xn are IID uniform on 0, 1 to the n. Right here, we can write this as vector notation. So that let's reverse that. If we say let's leave that. X1 to xn are IID uniform on 0, 1, meaning they all have the same distribution but are independent, right? It's like if you throw a coin or toss a coin 20 times, then you will have 20 uniformly random outcomes which are independent, given that you didn't somehow correlate your coin tosses. Whoops. Okay, good. Now, that's where I wanted to get at. If we have such IID x1 to xn, then we say the vector consisting of the x1 to xn is uniform in 0, 1 to the n. What does, so there's a question, what does uniform exactly mean? Uniformly random, which is also written here, we say that X is uniform form on some D if and only if for all X lowercase x in this set D, we have probability X equals X is 1 over size of D. Right? Means every possible outcome has the same probability. That's what it means to be uniformly random. I introduced this already in the last lecture, what it means that probability space is uniformly random. But here, let's just do it fully explicit again. Okay, good. Now, next example, this one is a bit more complicated. Let's take our IID random coins x1 to xn and add them all together. So we're adding them over the integers. We're not XORing them. We're not computing an XOR operation, but we're adding them as whole numbers, as integers. Then the resulting distribution y, which we obtain by this algorithm, right? The algorithm just consists of taking these base random variables, the x1 to xn, and adding them all up. Then the distribution of y, which is a deterministic function of the x1 to xn, right? But this distribution is called the Bernoulli distribution. And here you see an example of a Bernoulli distribution when we, I think this is when for n equals 16, right? When we add up n uniformly random coins, you will get this probability distribution function, right? And recall this bar here. This is just right. The height of this bar is probability y equals 7 in this case, right? And so forth. This is how we can specify a probability distribution function. So there's a question. Why does it look very similar to a normal distribution? Okay, anyone with a background in math or probability theory who can answer this? Surely someone here who knows the answer. Why does this look like a normal distribution? The reason is, okay, the central limit theorem. Let's maybe write that out. That's so important in math. Central limit theorem, which says, if you let n go against infinite, then this converges to the normal distribution. In fact, the central limit theorem says, give me any distribution of x and make x1 to xn IID to this x. X should still be bounded in some sense, right? Here it's really just the most simple random variable, namely uniform over 0, 1. But if you add many independent and identically distributed events on top of one another, if you kind of average them, right? I mean, adding up is kind of the same thing as averaging. If you add up small, independent, but identically distributed effects in a big system, then the resulting distribution converges to a Gaussian distribution, to a normal distribution. So this is precisely the reason why normal distributions show up so often in sciences, because adding up small and independent effects, you end up with something that converges towards Gaussian. Good. So this is the answer of that question is central limit theorem. Good. Now, something which matters maybe a bit more to a concept that which is important to this lecture will be sampling algorithms. So there's a question: can we take a short halftime break? I'm almost over with these slides, and before we start with the next ones, we're going to take a break. And the last concept I want to show here is something called sampling algorithms. So in general, we say that some random variable z is sampleable if there exists an efficient algorithm which takes as input IID uniform random coins x1 to xn and computes this z, right? So sampling algorithm is really just a computer program circuit. Think of your favorite model of computation, which takes uniformly and independent random coins as input and does some computation on it. Like here, y is a very simple example. This function or this algorithm just computed the sum of the x1 to xn. But in general, we can and will do way more complicated things with these input random coins. Okay. And here, typically we just say x1 to xn are the random coins, or just the coins of this algorithm n. Now, you went through the probability crash course. That's pretty much all you need to know. Those are all the tool sets, the basic tools of probability you will need to analyze the security of cryptographic constructions. But let's quit this lecture, which was the last one, as a matter of fact, with the following question. So someone asked this on Twitter. Probably you know this YouTuber, Grant Sanderson, also called 3 Blue 1 Brown. He asked this question on Twitter. What is the probability that 10 to the 10 to the 10 to the 1000th digit of pi is even? Is it 1 or 0? But I mean, we just don't know what it is. Is it 1/2 or is it something else? So with that, I'm gonna let you into a 10-minute break, and we'll get back at 35, at 1:35. See you in a bit. Okay, there still was a question. Does x1 mean that we tossed a 1? But someone answered that already. X1 is the first coin toss. Exactly. It's but the 1 doesn't mean that the outcome is 1. It's just the outcome of the first coin flip. Good. I think the next question has also been answered already. How is efficient defined for the sampling algorithm or crypto in general? It's the same definition as in computer science in general. We'll see that. We'll in an upcoming lecture, we'll quickly touch on what it means to be efficient. Spoiler, we'll mostly talk about asymptotics. So efficient will be that you're going to have a polynomial time algorithm, polynomial in the input size. Okay, but now getting back to my questions, maybe this would be a good thing for an actual poll here. Maybe we could. You know what? I'm just gonna put this as an ungraded question, so not giving you any points, into the next quiz. Okay, so next quiz, you're gonna be asked, what is your take on this? Precisely, is there a definitive right answer for computer scientists? Yes. Okay, good, but let's leave it with that. And let's go into the next lecture. Okay, so now that we're equipped with the tools of probability theory, we can start to do cryptography really scientifically, how it was initiated in the first half of the 20th century. So let's go back here. Essentially, until World War II, the design principles for ciphers were typically military secrets and not subject to open research or to public research. However, curiously, in World War II, especially the Allies recruited many civil mathematicians and engineers in their cryptanalytic efforts. Right, the most well-known case of that being, of course, Alan Turing, who worked for the British cryptanalysis effort in Bletchley Park. And now, those fresh minds that poured into this field soon realized that the central weaknesses of these back then contemporary ciphers, which again were military secrets, they were not known to the outside world, were that ciphertext preserved certain properties or invariants of the underlying plaintexts. Right, we've seen that, for instance, with the substitution cipher there, the ordered histogram of character frequencies is preserved. So that's one, in fact, efficiently computable property of plaintext and ciphertexts, which is invariant under encryption. Give me a ciphertext, compute the histogram, compute or encrypt it. Sorry, give me a plaintext, compute the histogram. Give me a ciphertext, compute the histogram. They will look the same. We've seen that. So even for much more, at the time, sophisticated ciphers, such as the Enigma, there were fundamental flaws in that for the Enigma, it was just a technical design limitation, or the technological implementation. They had to actually do that with rotors and wires, made it impossible that same characters or that a character, let's say an A, is encrypted as A. So A is encrypted as something else. And that tells you something about the plaintext when you look at the ciphertext, right? Like if the first letter of something of the ciphertext is an A, you know that the plaintext was not the first character of the plaintext was not A. And of course, these civil researchers and mathematicians, once they kind of came back from the war, this was also the onset of the information age, right? So until that point, until the 1940s, essentially all computations that were necessary for any given tasks had to be performed by hand. Most of them were performed by hand, but had to be performed by hand. So only like in World War II, with the advent of computers like the Colossus on the side of the Allies, or the machines of Konrad Zuse in Germany, which didn't see any action like for some cryptanalytic effort, we see computations being performed by machines rather than humans. And this is the beginning or the onset of the information age. And in math and computer science, this is marked by two seminal works of Claude Shannon, who you see on the right here, who sort of started the scientific study of information, right? Before that, information was an informal notion, but Claude Shannon actually managed to develop mathematical tools and a mathematical framework to work with this concept of information. Now, of course, in cryptography, we're trying to hide information. So information theory, as introduced by Shannon, was already an ideal framework to analyze the ciphers of the time. And Claude Shannon realized that himself. So in 1948, he introduced this whole mathematical framework of information theory. And in 1949 already, he applied this to contemporary ciphers, or to use this newfound framework to analyze and model the security of cryptographic ciphers of the time. Okay, now we want to talk about encryption schemes. We've introduced already encryption and decryption algorithms. Now let's add a little bit of extra formalism, which, spoiler, we're also gonna not forget but ignore very soon. So we've already seen encryption and decryption algorithms. Technically, an encryption scheme consists of three algorithms. There's also this keygen algorithm, which is a randomized algorithm which just produces a key K. So randomized algorithm means it takes as input, as auxiliary input, uniformly random coins. Okay, so this algorithm takes random coins as inputs and produces a key K in this set K. So we specify encryption schemes with these three sets. Set K, that's our key space. Now, encryption takes such a key and a message M and produces a ciphertext C, where the message M comes from this message space calligraphy M, and the ciphertext C is in the, what I could use different colors for this. So K, M is here, M in M, and maybe the ciphertext in red. Okay, good. So encryption is as before, just that we're kind of aware in what kind of spaces keys, messages, and ciphertexts live. And again, as before, decryption takes as input a key and a ciphertext, and outputs a corresponding plain text. Still really the same definition as before, only that we're making key space, message space, and ciphertext space explicit, and that we have this key generation algorithm which samples our keys. Okay, now, first property that we've kind of already looked or discussed about in the beginning is something called correctness. We say that an encryption scheme is correct if it holds for all messages M, that if we encrypt our message M with a key K and then decrypt it again, then we get back the same message. That's correctness, where K is produced by the keygen algorithm. Now, can we say something like that? The keygen algorithm is a randomized algorithm, right? So K is a random variable, and we've just learned things about random variables. They're not sort of fixed values, but here I'm making this look like this line here should always hold. So sometimes you write it that way, but that's formally not correct since K is a random variable. And when we say some statement with respect to a random variable should hold, we should always put this into a probability, right? This still kind of says the same thing, that this statement here always holds, but the probability, basically the correct way of writing this is probability that this holds is 1. Sometimes in abuse of notation, we're going to use the upper notation anyway. So here's a question: why don't we fix a key once with randomness, but then always use the fixed K to define correctness? You can do that, but it's actually better to do it this way, because if we look ahead a little bit, not this lecture, right? The correctness definition for encryption schemes can be relaxed by saying this is not 1, but say 1 minus epsilon for some small epsilon. It means we can have a certain correctness defect over the choice of the key. It means sometimes we choose bad keys for which certain messages in ciphertexts don't decrypt anymore. So the reason why we do this is just foresight. Maybe from your perspective, unclear why we have this foresight, but this is it turned out is a good way to define correctness. Just in that this definition will give us a way to relax it. Okay, there's another question. Could you explain again why the DEC whatever equals M notation is wrong? The reason why this is formally not correct, I wouldn't say really wrong, is K is a random variable, right? And then you cannot make a statement that says, oh, this is true for all, this statement is true for all M, when you still have a random variable popping up in the statement. In order to work formally correct with a random variable, you have to do something like putting a probability around this. And this is exactly what we did here. Okay. Good. This one point here is this, in general, this probability is taken over all the random choices involved, namely over the choice of the coins of keygen, enc, and if DEC is a randomized algorithm, which rarely happens, we would also say, I have to say, over the random coins of DEC. But for the cases that we will be looking into for the foreseeable next few lectures, only keygen will be randomized. I mean, we will soon see that encryption should also be a randomized algorithm to really get a strong form of security. But for now, we just think of keygen to be a randomized algorithm and both encryption and decryption to be deterministic. Okay. Now we're getting to the actual meat. See, we just have 10 minutes left, but we can still go into this. So now the question is, how do we define security? So we've kind of nailed down the syntax and correctness properties of decryption, of encryption schemes. But how do we now define security? So Shannon's idea was a security definition should guarantee that if an adversary gets to see a ciphertext, right? The ciphertext is typically something that we think of as public. I mean, if the ciphertext isn't exposed to an adversary, then already your transmission system, then you don't need encryption, right? So we need to assume the adversary gets at least the ciphertext. So if our adversary gets to see a ciphertext, he shouldn't learn anything about the message that this ciphertext encrypts. And the idea of Shannon was to really throw all he had in terms of information theory at this problem. And he kind of came up with a somewhat, really hard to work with a definition that included entropies of messages and ciphertexts. But the first question that kind of had to answer is, what should the distribution of the message be, right? In information theory, messages that are sent over channels are typically modeled as random variables. Like, I mean, we've seen random variables, uniform random variables, or let's say some distribution over sentences in English or in German or whatnot. And one thing you might ask now is, okay, what kind of messages do we encrypt? From what distribution do these messages come? Are they sampled from German, from English? I mean, Shannon's answer was, however you do this, however you model this, it should work for any distribution of messages. So it really shouldn't depend on what you encrypt. The encryption algorithm should still be secure no matter what is encrypted, which again, famously was not the case, for instance, for the Enigma. And here's a modern incarnation of Shannon's definition. So the way Shannon originally defined this in 1949 was probably a bit clunky and unwieldy, hard to work with. Right, so here we see a modern incarnation of this definition, which essentially says the same thing. So an encryption scheme, keygen enc dec, is called perfectly secret if it holds for any random variable m. Right, that's the important thing. Any random variable m that could, for instance, be a random variable that outputs English text. So for any random variable supported on the message space M, that's given that this random variable M and another random variable C, which is the corresponding distribution of ciphertexts, are independent, where K is chosen by the key generation algorithm. So writing this in a formal way, we say this just translates to it holds for all messages M in the message space and every ciphertext C, which has a non-zero probability of occurrence, right? Because we're going to condition on such a cipher on the ciphertext showing up. It should hold that the probability of M equals M conditioned on the ciphertext being C is the same as probability M equals M. So let's interpret this. I see there's a question. Whoops. So the question is, so intuitively that this means that we cannot get any information about the message when seeing the cipher. Correct. This is exactly where I was gonna go at this now. If we think of, again, this the definition of conditional probabilities and independence, what this means is that even if you get to see the ciphertext, from your view, the distribution, the posterior distribution of the message, right, after seeing the ciphertext is still the same as the a priori, for you as the same distribution as the a priori of the message. So getting to see a ciphertext doesn't increase your confidence that any particular message was encrypted, right? The ciphertext does not help you, which is definitely not the case for the Enigma, right? Just as we discussed earlier, we know that an A can never encrypt to an A. So if you get to see a ciphertext, you know that the first symbol of the ciphertext is an A, you know that the first symbol of the plaintext cannot be an A. Okay, there's another question. But doesn't all this depend very much on the quality of K and the algo that generated is? Yeah, I mean, of course, but when you say quality of K, we have, I mean, this is definition of what it means for a key generation scheme to be secure. The algorithm that generates K is the keygen algorithm. And for now, in the way we model it, this keygen algorithm gets perfect random coins that no one else gets to see, right? This is maybe something that's not explicitly spoken out in this definition, but we're gonna get there. So I think we're pretty much over in time. I mean, I thought I'd at least get to the one-time pad today, but that's fine. I mean, I'm ready to just take your questions now. So there is one question. With the Enigma, we know that the ciphertext cannot have been the plaintext, right? Exactly. That's another thing. This is true for every symbol of the ciphertext of the plaintext, but in particular also for the entire plaintext, for the entire ciphertext. Yeah. So quite obviously, the Enigma can never meet this this definition here, right? Because by seeing the ciphertext, you immediately learn something about the message. Not what the message is, but in this case, what the message is not. And that's already too much information that's revealed for this security definition to still be able to hold. Good. More questions? Again, typically at this point, when I would call it over, let's call it over, some people would still come in front to the counter during the lecture and ask some questions. So, I mean, in fact, since essentially, I mean, you can, if you don't want the others to hear this question, you can send it to me in private. All right, Zoom has this option of sending private messages to someone, and I'm just gonna read the question, but not who asked it, right? Which I typically do. I typically don't. Typically don't say who asked the question. So this is a private channel. Not perfectly secret though. Okay. Okay, I'm gonna stop the recording for now then. Thanks.